Okay, so our next paper is past generation for form additive manufacturing of large parts with cable-driven parallel robots. And the presenter is Elodie Paquet from Nantes University. And yeah, when you're ready, you can continue.
Do you hear me?
And I can hear you clearly.
Okay. Good morning, everyone. My name is Elodie Paquet. I work at the Nantes University, and today I present you a subject about power generation for foam additive manufacturing of large part with a cable-driven parallel robot. First, we present the context and the motivations, the proposal methodology, the cable-driven parallel modeling and the control, and the identification about the foam 3D printing modeling, the novelty of experience, the experimentation data, the result, and the conclusions. So at the Nantes University, we have developed a new technology for making a large part as the foam for the construction fly. In 29 in few work we have realized in Nantes an house of 80 square millimeter with a foam. So we print double curve wall, and after we fill in concrete. For what do you think we develop a new robotic solutions? We use in these presentations cable-driven parallel robot, because compared with the traditional robotic systems, cable-driven parallel robots have a large workspace that include the printing area. In addition, the potential of recoverability of the CD pillar is an asset to guess right of the collisions between the cable of the environment of the execution of a printing task. So we have made different tests and experimentation about the feasibility to print large part and large wall with this technique. Here you can see a wall. We have print about foam. The larger of the wall is 3 meters, for example. So the proposal methodology we use, we have make a modeling of a CDA pair foam 3D printer. And in parallel, we have make an identification and a modeling of the foam process. You can see it. We have take and we have create the trajectory, include the CDPR control, and we have make a different experimentation and validation to validate the solutions. So we use CDPR. So a CDPR is a cable-driven parallel robot beyond the class of a parallel manipulator, in which we have a spring and effector. Here is mounted on a moving platform, is driven by flexible cable interest in rigid links. So we have this robot in Nantes. The names of the platform is Craft, and the dimension of a platform is 4 meters by 3.5 meters by 4 meters here. The system is composed about 8 cable rolled in out on a which connect to be a frame, and we have a modeling platform. Here we have a tanks of a material. Here the workspace of a printing part we can print. And this is so the extruder. The extruder is controlled by a motor on the control of a CD player. For make a good generations and a good quality of a part, we have a print. We have a make a process identifications. So the process modifications we have obtained is interpreted by an experimental, as the table give us the layer height and the height of the layer. The process identifications is composed by an air alcohol. So here you have 2 materials, an isocyanate and a polyol, and a different mixing static mixture. When we print, the mixture is performed in a static mister, and the component is sprayed on the surface of the slab on a modern sub-layer as described. The material expands is a foam polyurethane. It expands about 5-6 seconds, and it acquires a sufficient thickness about 6 seconds to be good for a new printing of a new strat. The foam density is bounded about 3.35 kilogram by meter cube. After that, we have make different trajectoire generations. We will to print large scales of a foam. So we perform that angles to make the first test with a pattern generator. We have create a generator of a pattern in MATLAB for make a good trajectory, in particularly to regulate the printing speed versus precision of a print. The first time was printed in a polyline in order to see the conceptualities of a robot on a slow follow a rectilinear trajectory, and the test là staking. Voilà. The actuator of the CDPR control are controlled using a computer torque work control schemat with a joint spoke size feedback corrector. The integration of the model is performed inside the control leg on the cable-driven parallel robot. The control shapes is desired on the velocity and the spray on the head effector, VD, namely on the one on the moving platform along the deposition axis with begin and equals. The novelty of the approach for the new robotic platform for 3D printing with a large part with foam is an approach to fabricate wall or complex shape in building and constructions. So with 3D printing allow the use of the right amount of material and offer the ability to create complex and customized shape to use need and the structure and typology optimization on wall. The generation of complex geometry can be reductions of worker drawing, increase creativity for architects, optimize of acquisite thermal property of a building. So here you can see the first trial. So here you can see the moving platform. Here the tanks materials and the cables, and we have a print, for example, just here, the first layer on the trajectory. So we have a speed of 0.3 meter per second. So you can see that. It's just an example of 3D printing with a CDPR. Here we have a C and we have a change the trajectory, and we have a make a closed loop about this process to obtain a better quality. So you can see here the mobile platform. Here you have materials of materials. So we have a default of flatness on the strat, and we corrige the speed of the mobile platform to compensate in force light the flatness on the wall. So here you have a second steps. So you have okay. So the result, the test campaign discuss the proof Fruitland in experience, as well as a pointing of the difficulty of 3D printing of large tests, and show the great potential of cable-driven parallel for additive manufacturing tasks in construction sites. Both printing and comparison had a good results, and they show the capacity of the follow trajectory and the feasibility of a cable-driven parallel robot for large parts with foam is approved. So now we have to create, and we have a national platform, XXL Robotic, for the TLX European project. And we make a reconfigurable-driven parallel robot about a size of 24 meter by 6 meter and 14 meter. We have equipped this about robot and a robot and for create large parts in construction. So here you can see the CDPR used in TLX. So thank you for your attention. Here is the reference. Thank you for your attention if you have questions.
Thank you very much for your presentation. Very, very interesting. First of all, any question from the audience? No? Okay, I have plenty of questions. Thank you for, yeah, it's very interesting. So first question would be, do you need a reinforcement for the structure? Or the form actually can be structurally, you know, can provide the structure integrity for this whatever structure. You said the wall can be 3 meters tall. So does it, like, is it self-standing, or you still need to use a reinforcement?
We use a rigid structure developed in Nantes. So
okay.
It is an internal structure we have developed with a different laboratoire of research.
Okay. So yeah. So second question is yes, I'm quite interested about the how do you control the? I mean, first of all, the expansion of the form. What kind of a parameter, like external parameter, would influence the expansion rates or the expansion dimensions? Is it like humidity or temperature plays a role, or surely?
We have make modeling of the foam 3D printing process. We characterize the height and the weight of straight and the geometrical layer, the temperature inside the strats, and it depends of different factors, the speed of the printing, the density of the materials, the angle to be of the depositions, the height of the depositions, and another is the mixture or the ratio of polyurethane, of polyol and isocyanate. So we have a great model about with this parameter.
Interesting. So basically, all these parameters would also affect, let's say, influence the trajectory generation. And so can you? I mean, if I understood right, so you could, based on your research or the data, you could set up some kind of a pre-made recipe for the trajectory generation. Maybe in the future, like say, okay, based on this temperature, this material mixture, and this is the size of the, for example, the printing dimension in a way.
Thank you. Yes, for in the future, I think.
Yeah, in the future. Okay. Yeah, great. Thank you very much. Yeah, very interesting.
Thank you.
Yeah. Okay, then we move on to the next